Hello friends, I welcome you in lecture number 41 on Laplace transform. In this lecture also we will discuss two questions which was asked in GTU exam on finding inverse Laplace transform using convolution theorem. We have discussed about convolution theorem for inverse Laplace transform, and we know that if inverse Laplace transform of capital F is small f and inverse Laplace transform of capital G is small g, then inverse Laplace transform of the product of capital F and capital G is given by convolution of small f and small g. So we will remember this convolution theorem for inverse Laplace transform. So whenever we want to use convolution theorem for inverse Laplace transform, first we will write our function as a product of two functions whose inverse Laplace transform can be obtained easily. In this question we have to decide inverse Laplace transform of s square divided by s square plus a square times s square plus b square. This question was asked in GTU Winter 2019 exam. First step is, first we write given function as a product of two functions whose inverse Laplace transform we can obtain. Given function is s square divided by s square plus b square, and this I can rewrite as s divided by s square plus a square times s divided by s square plus b square. And I consider this first function as capital F and second function as capital G. Suppose this is equal to capital F into capital G, where capital F of S is S divided by S square plus A square, and G of S equal to S divided by S square plus B square. And we have ready-made formula for the inverse Laplace transform of these two functions, capital F and capital G. L inverse of capital F equal to L inverse of S divided by S square plus A square, which is cos AT, and this we will denote by small f of t. And similarly inverse Laplace transform of capital G is equal to inverse Laplace transform of S divided by S square plus B square, which is cos BT, and this we denote by small g. Now we apply convolution theorem. We are interested in the inverse Laplace transform of this function, which we have written as product of capital F into capital G. So now by convolution theorem we can find out inverse Laplace transform of product of capital F and capital G. We have to specify that we are using convolution theorem. By convolution theorem, inverse Laplace transform of capital F of S into capital G of S equal to convolution of small f and small g. We have obtained small f and small g, and here we write this f star g of t equal to 0 to t f of u g of t minus u du. This is by the definition of convolution, and here we substitute capital F and capital G, and here we write original function s square divided by s square plus a square times s square plus b square, and this is equal to integral from 0 to t. Small f is cos AT, f of t is cos AT, therefore f of u is equal to cos AU, and g of t is cos BT, therefore g of t minus u is equal to cos of b into t minus u. G of t equal to cos bt, and we require g of t minus u, So we replace this t by t minus u. So f of u is equal to cos au and g of t minus u equal to cos of b times t minus u du. So now we have to integrate this product, and we know we can apply the formula for this 2cc equal to c plus c. So here we require 2 in the product, that we can write by dividing and multiplying by 2. So we divide by 2 and multiply by 2, and this we rewrite as cos of bt minus bu, integral with respect to u. So 2cc equal to c plus c. So here we will use that formula 2cc. That means if we have 2 cos alpha into cos beta, then that can be written as cosine of alpha plus beta plus cosine of alpha minus beta. Here alpha is a into u and beta is bt minus bu. Now we use that formula and then we will integrate. So first step is cosine of addition of these two angles au and bt minus bu. So first we write cos au plus bt minus bu and plus cosine of subtraction of these two angles. We subtract this angle from au, that is au minus bt and minus plus bu, and we integrate with respect to u. So you can understand we are using this formula with alpha equal to a into u, beta equal to bt minus bu. So first we add these two angles, that is a into u plus bt minus bu, and we subtract this angle from this angle, so that is au minus bt and minus plus bu. Now we integrate this with respect to u, and we will remember that this t is considered as constant while integrating with respect to u. So here variable of integration is u. So before integrating we can write our function as cosine of, I consider these two terms which contain u. So I rewrite in this way, a into u minus b into u, that I can write as a minus b into u plus b into t. Similarly here also we can combine these two terms, plus cosine of a plus b into u minus bt. So we have rewritten by taking this u common. Here we take u common and we are left with a minus b into u plus bt. Similarly here we consider u common and we are left with cosine of a plus b into u minus bt. Now we integrate with respect to u. Integral of cosine of a minus b into u plus bt will be equal to sine of a minus b into u plus bt divided by coefficient of u, which is a minus b. And similarly integral of cosine of a plus b into u minus bt, that is going to be sine of a plus b into u minus bt divided by a plus b. Limits of integral are from u equal to 0 to u equal to t. Now first we put upper limit, that is we replace u by t, and we see what we obtain. So here we can replace u by t, that is a minus b into t, and that is going to be at minus bt. So here we write at minus bt plus b into t. divided by a minus b. Similarly, here also we replace u by t, and we will see it is going to be a plus b into t, that is at plus bt. Sine of at plus bt minus bt divided by a plus b. Lower limit is u equal to 0, that is, if I take u equal to 0 here, I will have sine bt divided by a minus b. Similarly, for u equal to 0, I will have sine of minus bt divided by a plus b. So this is for upper limit. And now we write for lower limit, that is for u equal to 0. For u equal to 0, we have sine bt divided by a minus b. So let me write it first, sine bt divided by a minus b. This is for u equal to 0 in this term. And if we take u equal to 0 in this term, we will have sine of minus bt, that we can write as minus sine bt, and divided by a plus b. So here we write minus sine bt divided by a plus b. This is for u equal to 0, that is for lower limit. Now this we simplify. Here bt will cancel out and we will have sine at upon a minus b. Same thing here, bt will cancel out and we will have sine at upon a plus b. So first we write this, sine at upon a minus b plus sine at upon a plus b, and 1/2 is there, sine at divided by a minus b, and here we have sine at divided by a plus b. After we cancel out this, sine at by a minus b, sine at by a plus b. So first I write this, sine at by a minus b, sine at by a plus b, and here we take this negative sign inside the bracket, and we will have minus sine bt divided by a minus b, minus minus plus sine bt divided by a plus b. So we have obtained this after we put upper limit and lower limit. Now we can take sine at common, and we are left with, suppose we take sine at common, then we will have 1 over a minus b plus 1 over a plus b into sine at, and here we take sine bt common, and we are left with 1 divided by a plus b minus 1 divided by a minus b into sine bt. We are just trying to simplify as much it is possible. Now we take LCM. LCM is a minus b into a plus b, that is a square minus b square, and in the numerator we will have a plus b plus a minus b into sine at. Similarly, here also we take LCM, a plus b into a minus b, that is a square minus b square, and here we have a minus b minus of a plus b, that is minus a minus b into sine bt. And let us see what we can do further. Here b will cancel out, and we have 2 times a into sine at, and here a will cancel out and we will have minus 2 times b into sine bt, and denominator is common, which is a square minus b square, and again we can observe, we can cancel out these two, and finally we have a sine at minus b sine bt divided by a square minus b square. This is the inverse Laplace transform of given function, which was s square divided by s square plus a square times s square plus b square. So we have used convolution theorem for inverse Laplace transform to obtain the inverse Laplace transform of this function. Another way is we can use the method of partial fractions, but if it is specified that use convolution theorem, then you must do the problem using convolution theorem only. Here it is not specified that use convolution theorem, but we have done this problem using convolution theorem. If you wish, you can apply the method of partial fractions to find out the inverse Laplace transform. Suppose we are going for method of partial fractions to obtain this inverse Laplace transform, then we can see there are two quadratic factors in the denominator, so we can use the partial fraction decomposition. For a square plus s square, we have to write a into s plus b, and for s square plus b square, here we write c into s plus d, and we have to decide the values of these constants a, b, c and d, and then we can obtain the inverse Laplace transform using this method also. Here I have obtained this inverse Laplace transform using convolution theorem. You can do as an exercise that find the inverse Laplace transform of this same function using the method of partial fractions, and you can compare your answer with my answer and you will get the same answer. So in this way we can obtain convolution theorem to obtain the inverse Laplace transform for product of two functions. So it is very easy. You just have to write your function as a product of two functions of s whose inverse Laplace transform can be obtained by using earlier methods or by some direct formulas. And once you obtain the inverse Laplace transform of those two functions, then inverse Laplace transform of the product is nothing but convolution of their inverse Laplace transform. So this is another way of obtaining inverse Laplace transform. If you wish, you can apply convolution theorem, or you can use this method of partial fractions also. So this is all about this session. I hope you like it. Thank you very much.